prefer talking with my hands, and it works better now. First of all, I'm very glad about the previous talk about Sundo, because not only because it was an excellent talk, but also because I was thinking how to structure my talk. Because on one hand, I want to give a global overview of the global problem is from an industry perspective, and what methods are, and etc. On the other hand, I also want to show some concrete examples, and somehow that didn't fit in 25 minutes. So I decided to focus more on the concrete examples and dive a bit more into detail. And so I'm very happy that you give this excellent introduction to the topic. And frankly, I think, of course, we are very different companies, but I think the view on the problem is very similar. The methodologies, the steps to take, of course, all the details will be very different. But the general picture, I think, is very similar to the approach we have. So this allows me now to step a bit faster to the details. Let me first say something about myself. My name is Bruno Schürmans. I work for ALSTOM in Switzerland. We develop gas turbines, so end-based stationary gas turbines only, so no aero engines. Of course, we also do other things. ALSTOM also builds trains and electricity distribution networks, and whole power plants. But I work in the gas turbine business, and I work in the development of new gas turbines in combustor department, and my specialty is thermoacoustics. And so I will show you what kind of methodology, or some examples of methodologies that we use on developing gas turbines that at the end are stable and don't cause us too many troubles. And I must say, I really highlighted some topics here. Of course, we do much more than that. But first, brief introduction to what kind of engines we have. These are the four products we have, and we have this since quite a while. The names don't change, but what's in it changes over time continuously. Power upgrades, efficiency goes up, and emissions go down. These are the G26, our largest engine. Is there a pointer somewhere here on the laser? Oh, there's a pointer. If someone has a laser, I can do like this. So G26 is our biggest product and has a sequential combustion. I will show you a bit later, and this talk will focus mostly on examples of the G26. So this is quite unique technology where we have this is compressor, first combustion chamber, high pressure turbine, and then a second combustion chamber and a low pressure turbine. I think that is a unique ALSTOM technology to have this sequential combustion, as we call it. It gives the reason why we have it. It's first you get more power for the same size of engine. Secondly, it's very flexible because the second combustor you can just switch it off. Also because this is an auto-ignition process, the combustion is much easier to control. You just, okay, you just, I didn't start talking about the reliability of engines and all these things. That would have been the perfect timing, but okay. So the second combustion chamber, you just inject gas in these hot streams, and then there's auto-ignition, and so that's quite flexible. You can dump any gas in there, it will burn after a little while. Of course, if you need less power, for example, in an area where there's a lot of wind industry and the wind energy and the wind starts blowing, you can just stop the gas that goes to the second combustion chamber. You still have low emissions, you still have the right combustion efficiency, etc. So it's a very flexible way of very flexible gas turbine. This is a bit what it looks like in an exploded view. We have this our EV burners here. So there's a premix type combustor where fuel and gas is mixed in this burner or swirler, as we would maybe call it, and we have a vortex breakdown. Better like this? Yeah. Okay. Vortex breakdown taking place here. Here's the first turbine, high pressure turbine.
And this is the second combustion chamber. This preheat combustion chamber. This is the fuel end. Fuel comes in here, and it's the second zone of heat release. What I'm talking about today will be about this first combustion chamber and what kind of models we use to predict the thermoacoustics in that combustion chamber. Of course, our customers at the end, they don't care too much about thermoacoustics. We care, but it's mostly because we want to achieve lifetime, and that's why you don't. And that's also what the customer wants to have. And to achieve lifetime, you don't want to have too high pulsation levels because that reduces your lifetime. And also in terms of operability, pulsations are above a certain threshold. The engine would simply trip, and you want to avoid that. So the lower your pulsations are, the more flexible you are, and the better you can operate the engine. If it comes to new combustion technologies, NOx emissions are a very important aspect. And in essence, it's quite simple to achieve these low NOx emissions, because given the amount of gas and fuel that you have, you just have to make sure you mix it very well and you have low NOx combustion. But in practice, the biggest constraint to that is that if you do that, you will see that you get quite high acoustic pulsations, or at least you have a big risk to get these high acoustic pulsations. And then in practice, what you need to do then is to do some staging, or you have to do to operate your engines at conditions where you would normally not do that. And that is typically where you get higher NOx emissions again. So really, to achieve low NOx emissions, you need to get the thermoacoustic pulsations under control. I need to be able to predict them in a very early design stage in order to really do something about the problem. So how do we do that? So here's the process, how we go about. So we start with a certain design, and then we break that design out in different parts, and we start build up a model of that. And some like the combustion chamber volumes we can model with finite elements, and then we have a trick how we can use these modes in a hybrid thermoacoustic network model. And as we've also done from the previous talk, these transfer functions, or we use transfer matrices measured, or from CFD, or from models, are crucial input to these kind of models. To do something about the pulsation, I mean, if there's danger or risk that there's pulsations, we add dampers into the combustion chamber, so we also have to put them into the model. So we put all this together in the model, we do an analysis. There can be eigenvalues, stability maps, time tracing. It's quite flexible. I will show you how that works later on. And then, well, if it's fine, we're happy with it, and that would be then a reliable solution. If we see that things need to be changed, we can change it in the model, and we go through this loop. And of course, then it's going to be tested, and we see if it works fine like that. So here's basically the same information. So we, on the previous slide, this is a screenshot of the tool that we use. We use input, so input from finite elements, and the only input that we need is the mode, so the acoustic mode shapes and the eigenfrequencies. And we need that only of the combustion chamber and the planar volumes or other volumes that are there, with solid wall boundary conditions, but with the right temperature distributions. Of course, in reality, you will have a certain impedance here, you will have impedance boundary conditions there that are extremely important and are absolutely, to stress, not neglected in this analysis, but that will be imposed later on in the model. Now to this measurement of transfer functions. This is a setup, and we have that for over more than 10 years. That's a picture of here, and what it looks like. It's like a supply tube of air. The burner is mounted here. This is the combustion chamber tube with speakers upstream and downstream, and arrays of microphones upstream and downstream. And we send signals to the microphones, to the loudspeakers. We record and pulse the response with microphones. And from that, we can extract a transfer matrix that relates the acoustic quantities upstream and downstream of the burner and the flame. And very important, and that's really the thing also that I want to stress here, and it's often not mentioned, we also measure the source terms. Because the transfer matrix relates the inputs to the outputs on both sides of this burner flame element, but the flame also produces sound by itself due to combustion, turbulent combustion, and it produces also noise, which is not a result of an input to the system. So it's really an independent source, and we measure that as well. Now with this method, we have, as I said, more than 10 years experience. It works in a very robust manner. It's all optimized, so it's really used in our development process as a standard tool. We put the burner in, we press a button, and the whole program goes automatically, and the whole post-processing, etc. And in a day, you get 20 to 30, even more, of these transfer matrices and source terms and everything measured. So we are very happy with that setup, and that's also not changed a lot over the years. But now, what do we do with them? So because we measure these transfer functions, and well, that's forgot to mention that these are frequency responses. You get these matrix elements, a complex value and functional frequency, but you have to somehow put that in a model. And what we used in this network model is what I call it's based on state space modeling. It's a way on how to express linear dynamic systems. And so we fit to these measured transfer matrices and source terms these state space models. Now here an example how we derive a state space model for an acoustic volume. So any acoustic volume, no matter how complex it is, we model it in finite elements with solid wall boundary conditions, and from that we get this mode shape, this psi, and the resonance frequency, omega n. And that's the only thing that we need from the finite elements computation. Then you can find, I won't show how it's derived, that you can get an input-output relation to some of that volume. So the output would be this pressure, and the input, the velocity that you impose somewhere on the boundaries. That this equation gives the input-output relation to any pressure measured somewhere in the volume to a velocity applied to somewhere on the boundary of that volume, or it can be multiple pressures and multiple velocities. I mean, but the whole thing, this is kind of a series of second-order resonators, so linear resonators, and this you can express then as in one of these resonators as two first-order, a couple of first-order systems, and that would pack then a whole matrix, and this would be big matrix elements with all the resonance frequencies and some damping terms, big matrix with all the modal, the values of the modes on the boundaries. Well, don't need to explain the details of it, but we have a very structurized way to go from finite element to an input-output dynamic description of any volume, no matter what its complexity, as long, well, only described by the Laplace equation. So here there's well, there's some damping, but no physical damping included, no heat release, etc. So it's only one part of it. But then we have many more parts in a realistic system that we want to combine somehow. For example, we would have a burner, we would have a flame, a combustion chamber, an exit, and a plenum. And remember, these are, well, disconnected with arrows, but we talk about annular combustion chamber, so you don't have one burner, but this would be maybe 20 burners or 30 burners and 30 flames, etc. The combustion chambers would be multi-input, multi-output kind of blocks. But we can all describe that with either this expansion that I showed on this slide. So we got these equations described then, for example, the plenum or the combustion chamber. We have these measured flame transfer matrices. We fit state space equations to that, so we have that. And from the burner, we have some analytical, partly some analytical expressions, and we have some analytical expressions for the exit condition. And then we use a method that's standard in control theory. It's this red heifer star product, which you can very conveniently combine all these different submodels into one big model that combines everything. And at the end, you get, again, a very simple equation with some state equations. And so this is the time derivative of the state. It gets updated, again, by the state, multiplied by some matrix A, that somehow where all this information is compacted together. As a response to some source terms, and so this US would always be the source to the system, so really the physical source driving the system. That can be turbulent combustion noise typically. If you would have a loudspeaker and a test rig, then of course you would have somewhere here a thing that represents this loudspeaker, but in a gas turbine you don't have that. And then what you measure, well, I'd say what you measure or what the quantity you're interested in, for example, pressures at different locations, at every location, no matter what, or you can also velocities, whatever you're interested in, you get that as a map of the state vector X via this matrix C. So it's a very generic, general description of expressing dynamic models. Well, I explained this already, but in words, so this is what the interconnection looks like in the Simulink network diagram we use. We have this planning, we have the burner. It's a partly, so the burner introduces a lot of resistance. There's a lot of losses induced by the burner. This is measured, these losses are measured, and then we have a model that describes that. But the reactance is just modeled as any other volume based on finite element expansions. Then we have the flame. Well, this linear part we get from this state space equations fitted to the measured flame transfer function. However, the nonlinear part, there we put in a simple saturation function. Physically, this is not really correct, but we don't have means to do that more correctly. I will come to that point later. The source, we have measured it explicitly as a function of frequency, and we fitted some, because this model runs in time domain typically, we produce some white noise, and we send it to a filter such that the noise that comes out of that filter is exactly the same shape of the noise that we measure. So a very realistic representation of the physical noise in the system. Well, then the combustion chambers, and again the state space expansion of these finite element modes, and then the turbine inlet. Well, it's not shown here. There's some real valued impedance based on analytical results. Well, I won't go too much in the details of all the things, but typically we have this very generic expression, and it can with that you can describe all the dynamics of the whole system. There's also this nonlinear part in here, which is in our models not described physically very well, I fear. If you only consider on the linear part, so not considering this thing, then you can do an eigen analysis, so the eigenmodes you get from the eigenvalues of this matrix. You can look at stability of the system. You just have to make sure then that the real parts of the eigenvalues are smaller than zero. You can extract mode shapes. The mode shapes, basically you get them from the eigensolutions. So the eigensolutions give you the eigenfrequency, but also the eigenvectors of the states, and basically you have then to map the eigenvector of the state via your output matrix to measure your mode where you want to have it measured. Well, frequency response, time response are straightforward. If you want to solve the real system with the nonlinearity and the sources, you have to integrate it, this whole system, numerically. Oh, wait a minute, time.
You're okay on that.
Yeah, no, but that's you don't know that's still coming.
We're ready to do it, we're not okay.
Okay. I want to show a simulation, but maybe I leave that.
Sure, go ahead. No,
Just to have an impression on how these things work. So this is one of these networks, so I should now you can't see anything. Here's then the time traces of some pressures that I measured. So it's, I don't know, it's like 20 signals, so it doesn't look very interesting. It looks very noisy because there's a lot of noise. Actually, there is a slightly unstable system. They don't really see a very clear limit cycle. We can also look and decompose these annular modes. Well, let it run again. Here you see every of this plot, every of the colors is the amplitude of one of the circumferential modes. I basically do the post-processing online, and then you see the light blue curve is the highest, and well, I know which one it is. I think it's the second azimuthal mode. It gives the highest response, but also all the other modes give some response. That's quite typical. You have some fields at different modes, and they interact and etc. Of course, once you have these results, you can do a lot of post-processing and go and analyze them. And you see it's simulated now 10 seconds of real time. It goes quite quickly, a couple of seconds or what. A bit slower than real time, but it's a very efficient way of calculating things. Okay, based on the simulation that I just showed, we did that for a real case and compared the results with measured spectra of a real engine that is running at a customer. And we did the predictions before we did the measurement. However, I come back. There's some coefficients in the prediction that have been tuned to previous data. So it's not a truly 100% prediction. I put that as a disclaimer. But if you see its prediction, these are the spectra that have been predicted. It's a prediction, and here you see the amplitude of these peaks. Then you see different curves, and we changed the flame temperature. Now we collected the amplitude of this first peak here, and I plotted over flame temperature. You see, so this first peak, it goes normalized. It goes down with flame temperature. The second peak goes up with flame temperature. If we now look at the measurement, we also have this first peak that goes down with flame temperature, the second one that goes up with flame temperature. However, it doesn't go up that high on both sides, but you also have to see with the prediction, we went further, in the further range of flame temperature, so maybe the shoot up that you have here, maybe it would come here or not, we don't know, because that's of course the thing, in a real measurement at the customer engine, I would be very interested to see what happens. So if you push up the flame temperature here, does it shoot up there? But of course, the customer would be less interested to see that, and that's why we generally have more this kind of data with less extremes. And I think that's a quite important thing, because generally, of course, our products are designed to be stable, and here they are stable, and really on these borders here, it's on the verge of becoming instability. And this is typically the range where gas turbines operate. They don't operate generally in the point where it's very unstable, and also not where it's very, very stable, because there's always this trade-off that you want to reach between NOx and pulsations. You're always a bit on this edge of stability and instability. But then, sorry. So often we are on a range where that is quite stable, and then okay, it's stable, the eigenvalues are fine, so there's no problem, but then this guy will complain. And it says, no, it doesn't work like that. You can also have problems that even if you have completely stable eigenvalues, that all of a sudden things start growing. And if, well, we didn't look in the time to haste in detail, but sometimes you see some kind of bursts of things that go up. Well, I don't have experience that they go dramatically up, but still only relying on eigenvalues if things are stable is not that safe. But then you could say, okay, we do time domain simulations, everything is contained in there, so that's then any of these exotic non-normal effects are in the model. They should all, well, they are in the model. You should see them in the time traces, and so it would be fine to analyze these time traces. However, the simulation goes quite fast, so we can get 10 seconds, we can get the minutes, we would get minutes. But typically what you have in this kind of system, you have a very small probability that something can occur that reaches to very large amplitudes. And you don't want to run any simulations for, I don't know, for ages and ages to see if such a thing could occur. And so, with interest, read a lot of publications of the past years on this non-normality, how we can characterize energy growth, etc. It somehow didn't fit exactly with the way how I wrote my equation, so I adjusted the equations so that I could use it, and basically you want to extract the energy in the system. Now, you can with some, express these etas are the modes, or the modal amplitudes, and the time derivative in the acoustic modes and in your biggest volumes. You can get the energy as a sum over the square of the mode and its time derivative. And then you can, in the state space machinery, you can always define a certain matrix C that multiplies the space vector X, so that you get exactly the quantities that you have in here. And if you do that, then you only need to take the norm of this thing, or the norm of that thing, and that gives you the energy at every instance of time. And then with that trick, I was back again to the equations as I found them in literature. At least I thought I was back there with some problem with that. And then we could use machinery that all the people use with singular value decomposition, etc., to find the largest energy and the state vector that would bring you to this big energy growth. And yeah. So instead of we have this matrix B. That is our input matrix. Remember, it describes how any of the source terms, how they affect the system. But it doesn't need necessarily to be the physical source term. Does have to be a loudspeaker. If it's a little reiki tube, it can be someone snapping with his hands. You could kind of model that in there. You could also model any initial conditions of the system in there. So it's quite general. But then the question is often in reality, what is really a right choice of this matrix B? Now, if I look on this road, if I first look at the energy that's in our system, so that's the first thing I did, and I've got this energy normalized when it's at time 0. And there's a logarithmic scale, so this is very small time. But first you see kind of growth of the amplitudes, and afterwards it decays and then remains 0 forever. And they say, you have to be very careful if you have such a situation, which can indeed have this non-linear growth. And this is just the example which I showed the simulation before. It's not dramatic, 50%, but still, I mean, maybe there's other conditions where it's much worse. However, when I started then thinking, what is really the physical? Because here, with this definition of this non-normal growth, basically I can put my state vectors in the worst possible situation to have this growth occurring. But then the question is it physically possible to put that state like that? And also, what's not really a fair thing to do is basically the energy doesn't use all of the states, because there are so many states with all this fitting to measure data. There's a lot of unphysical states. I don't know, it's not just modal amplitude, etc. There's a lot of things. So if they're not all used, it's not really I don't think it's a really fair and a good norm to put in there. So then I said, okay, if I now really rely on my model and on the inputs that I have in the model, and then I say, then I know that these inputs should be in this US, that is how I modeled the sources, and then it could only be a worst case situation on how the sources are configured. But if I look then at the norm of that thing, then there's not such a normal growth, because I start one, it happens off. You have this little thing there, but this is of course very, very restrictive. It's not an perturbation of the initial condition, but somehow to find the real, the right physical inputs and then the right physical interpretation of the energy is somehow tricky. And maybe now expect me to show the next slide where I show how it should be done, etc. And that's not. But I really like this as an open question, maybe also for discussion further on. Also, really to see, is it really the energy that we're interested, should we evaluate the energy, or isn't it that we are more interested that we have this non-normal growth, reaching high amplitudes, triggering some non-linearity, and then kicking off something that remains at this high energy. If that's really what we worry about, shouldn't we then more try to evaluate what amplitude really triggers this nonlinearity and see if this amplitude can be reached or not? Will be this, yeah, will be the source, and then we invert with our measure transformator, we invert the thing, and you can. But of course, if you do that, well, I call it source term. But if there would be any nonlinearities in your in the physical model, these nonlinearities that would end up in the source term. Also, if you make some errors, some identification errors, that would also somehow indirectly end up there. Okay, so I started to discuss that these stochastics are very important, and you cannot really see it as separately as either nonlinear limit cycle or stochastically driven equations. And if you now look at a simulation how these things are measured in engines, so that's what it's all about. Then I should first explain what we have. This is our real engine data. That's to say, it's an annular combustor, and we had 1, 2, 3, 4, 5, 6. You see sometimes more that starts rotating itself. It's a rotating mode, and then it kind of stalls. It starts being a bit a standing wave, and it continues in the other direction and starts being a rotating wave. So now it's a standing wave motion, more or less, and you'll see that slowly it will drift away from that, and it'll start rotating. Yeah, see now it starts rotating again. At a certain point it will stall again and will rotating in the same direction or the other direction. So there's a lot of interesting dynamics behind it. And of course this is very important for us to know what's behind this, because here we have the luxury of having 7 probes. In the typical custom engine you only have 1 probe. And with 1 probe, you cannot tell is the standing wave or is the rotating wave, because you just see a fluctuation. If it's a rotating wave, then at least you know that you get the amplitude right, because it will be kind of uniformly distributed. So no matter where you put the probe, you'll have the same amplitude. If a standing wave, you don't know if you get the amplitude right, because if you put the probe on the maximum, you're fine. If you put it on the minimum, it's wrong. So there's a lot of debates on what the nature of these modes are. And I did a long time ago theoretical analysis and also observations on our tools, is that in a limit cycle these would always result in rotating modes. So I would just say, okay, it's unstable, it's a rotating mode. So that would be my statement. But I was not really right, because you see sometimes it's rotating, sometimes it's standing, sometimes it switches, etc. And so what I want to show further then is basically an analysis of these kind of modes. And this behavior, you get it really because it's a stochastically driven nonlinear system. So I've shown these modes, and basically these modes you can see them as 2 at every instant of time, see them as 2 rotating modes going opposite direction with different amplitudes, or you can see it as 2 standing waves, each with this amplitude, one with more like a cosine distribution around the circumference, other more like a sine distribution. And this, so one will have a cosine distribution around circumference and the other sine, and they have a time varying amplitude which varies sinusoidally. I didn't put it in the grid, but basically this amplitude A of this mode and this amplitude B also changes in time, but much more slowly than the acoustic time. And so this A and B we extracted from the data, from these measurements that I showed before, and then you can plot joint probability density function or histograms or PDFs of that. So you plot A on the axis there, B, and basically, that was our first step. We would always have thought that the maximum of this distribution should be so on the diagonal, or say that A and B should have equal amplitudes. They have not. That means that in the data that we analyze, that means that there's some asymmetry. Okay, we found data. Then we can plot the phase of this A with respect to B, so the A mode to the B mode, and you see it's quite a bit distributed. It would be a purely rotating mode. It should be either plus pi over 2 or minus pi over 2. You can work that out on quite simple considerations. You see indeed that there's a maximum of distribution.
plus pi over 2, and also some kind of maximum plus minus pi over 2. It's quite distributed between the two. So it's something in between. It's not a standing wave, not a rotating mode, but it has more a rotating character because the maximum is that pi over 2 phase and the fixed phase relation. If I extract the same plots from my simulations, from my acoustic network model, then I did that for 3 cases. One which was pretty stable, but it's all very realistic cases, and one which is probably most realistic, so as you would an engine would operate, and one which is a bit higher, but still not extremely high. And then you would see that in the stable plot, first of all, you see everywhere that the maximum of this A and B distribution is always on 1 and 1, so equal amplitude, and it's all normalized, of course. But for a very stable case, you have a very uniform distribution of the phase. Well, these borders here are just the way how I plotted the data. But basically, uniform distribution between A and B means that these A and or the sinusoidal parts and the cosine part of the mode are independent, randomly stochastically fluctuating. If you go more unstable, they concentrate more around this pi of plus and minus pi over 2. Means that they get more a rotating mode character, and if you continue that, it becomes more and more, and you could imagine that at the very end you can just really get dots there, and it's really a very unstable limit cycle oscillation. So now we understand, well, this is what what the experiment corresponds with what our numerical simulations show, but we still don't really have an understanding why this is and what's behind it. And then what I did is, okay, we have this whole model, but there's so many states and things and whatever, something comes out, but then what is really the key that's behind this? Well, if you look at the spectra of this oscillation, you just see one peak, so it means one frequency. We know that for these two frequencies, there's 2 modes, one the cosine shape, the other sine shape. So basically, would tell us we can reduce all of these in this whole system, as hundreds of states, we should be able to put that down to just 4 states of two oscillators with 2 mode shapes. And then from the state space analysis, I will not go into detail. You can have a very elegant way of going from the full model to a very strongly reduced model, basically on on calculating the eigen modes of the system, and then projecting this large state vector only on these eigenmodes which you're interested in. And these are just these 4 eigenmodes. So we have done this model at the order of in the hundreds to a fourth order model. And this fourth order model is nothing else as two coupled linear oscillators. And it turns out that the coupling of these 2 oscillators only occurs via the nonlinear elements in our system, if the system is completely symmetric. Oh, sorry. Well, and then, because there's nonlinearity, I said that's a bit the weak point in our analysis. We don't know really what this nonlinearity is, but if we put some saturation function in it and adjusted 2 values that the final limit cycles make sense. Well, but it also turns out that if you express such a nonlinearity as any whatever polynomial expansion, well, first we're only interested in the real nonlinear terms, so the linear part we don't need. In the averaging method that we'll use later, the quadrat or the even terms, they go out, so the fourth and the second and the fourth order, we don't need, they disappear later on. And then, so if you expand this nonlinearity up to 5th order, we only need to retain the 3rd order terms. So you have quite general description, and you only have one coefficient, the C3, and I think I call it K kappa later anyway, that characterizes the nonlinearity in our, the saturation nonlinearity in our system. And then, well, we consider only then the 2 modes, as I said, that describe these orthogonal oscillating structures at the same frequency, and we substitute an expression for that. We put that in the reduced equations, and then now I'm making big steps. We apply deterministic and stochastic averaging to these equations, and at the end you get equations that describe how the amplitudes of these 2 modes evolve. And there's a linear part, and so if it's unstable, this linear part, this will be positive, so it means that this thing will grow if this thing has a certain positive value. And the coupling between the growth of A and the growth of the B amplitude, there's some non-linear cross terms in there. And what's in these boxes is the stochastic contributions to the equation. So if you average on the stochastic fluctuations. If you ignore the stochastic parts, so what I did in the past, then you can solve these equations and you will see that the only non-linearly stable solution, or an attractor solution, is a case where A equals B, and where the phase between the two is equal, plus or minus pi over 2. That means a rotating mode. However, we know more now. We have these boxes also explicit here, and that describes really explicitly how the stochastic influence these modes. And once we have these equations, we want to compare these equations with the data that we have. Well, we have A and B, right? We have the derivative of A, we just calculate from direct numerical derivative. This kappa, which is actually this C3, describes the non-linearity. We don't know. We don't have a good model for that. And what really the amplitude, this term is the amplitude of the stochastic driving term, we also don't know. So basically, only from all these equations, only three things that we don't know. And so what we're going to do, we're going to plot the distributions of A and B, of the derivatives of A and B versus A and B, and then fit this model to it, and then just fitting these coefficients that we don't know, so that this nu, which is the linear driving term, and then this k, which is the nonlinear term, and the noise term. And now let's say fitting, basically we came to the idea that you can describe these equations as the Fokker-Planck equations, and then you can compute explicitly these coefficients, but that be aside. What you get if I plot this A prime, which is a function of A and B. So here the values that is seen here is just a plot obtained from the data of this engine, so A, B, and then its amplitude. And behind it, it's not very good. You see the smooth surface. That is the fit of our equations to the measured equations. And you see that the fit characterize this dynamics quite well. So I think. Yeah, and the fact that the model fits these measured distributions quite well means I think that we have well characterized these nonlinear dynamics, although we have done a tremendous reduction of the problem. We have a very, very big model, and we reduced it, we really cooked it down to the absolute minimum, but I think this is just, well, we cooked it down to the absolute minimum, but not further than that. We still contain all the relevant aspects. And now we can solve these, because these parts are basically multi-dimensional probability density functions. We can solve these now analytically. We can solve for these probability functions. We need to do some assumptions, and I won't go into that because now we're running short. But if we do that, then we compare these distributions for the real data with the analytical solutions of these reduced equations. We get the value, so this is what's measured, and this is what this analytical solution would be with the simplified model. And I think with that, say we have cracked the nut of this rotating, standing rotating mode dilemma. We understand the stochastic speed behind it. It's all randomness, but we understand the randomness. We understand how it interacts. But what's even better about that, by doing these fits, by fitting these equations to the real data, we obtain this linear driving term, and we obtain this linear, non-linear saturation and the noise driving term. But these three parameters are extremely important because they really characterize the entire problem that is at hand. First, it tells you about the linear instability of the problem, how strongly unstable is it. First, it tells you something about how it saturates, and third, it tells you how much it's driven by noise. And these three quantities are exactly the quantities that you would need if you develop pulsation abatement strategies. If you want to develop dampers, you need to have these quantities. So we're very happy that we can do these fits now to real data, extract these quantities. It's very abstract quantities, but they have a very important relevance on finding pulsation abatement strategies.